Okay, today my plan is to talk about non-Abelian statistics. And also, if possible, also on beyond Majorana fermions, so fractionalized versions of Majorana fermions. Okay, and I'll have to do this without the privilege of saying that we'll do this in that next lecture. Right, so maybe I'll at least try to comment on the fractionalized Majorana fermions at the end. Just to remind you where we were. So we were discussing a topological superconductor. So either a P plus IP 2D superconductor. So suppose we have a 2D system and there's some number of vortices in it. Okay, so n of these vortices, or we also found a similar structure. So every vortex core carries a Majorana zero mode below, which is bound below the gap of the 2D superconductor. And in 1D, you can also actually realize the same phase. I mean, it's not the same phase, but you can have a very similar phenomenon. At the end of the wire, you'll get Majorana zero mode. Okay, and if you have n over 2 of these wires, then total there are n Majorana zero modes. And there's a gap in the system, but there's a low energy Hilbert space. So the ground state of the system in the presence of these n vortices, for instance, is going to be a degenerate. Okay, so if there are n Majorana zero modes, the number of states in the low energy Hilbert space is going to be 2 to the power n over 2. So the way to understand that is that every pair of Majorana zero modes are form a single complex fermions, a fermion that can either be occupied or empty. And as long as all of these Majorana zero modes are far away from each other spatially, then these states are going to be almost degenerate. Okay, they're going to be degenerate up to a splitting, which scales exponentially with their separation. Okay, L over xi, where xi is some characteristic length of the system. It's the length over which these zero modes decay. Okay, and then the rest of the spectrum is actually separated by these quasi-ground states by a gap, by a finite gap. Okay, and so these are our states, and they're very unusual states. Okay, they're to first approximation exactly degenerate. Okay, it's split by a tiny amount. But they're non-local. Okay, the information is stored non-locally. You can't do any measurement, any local measurement around each one of these Majorana zero modes, and know from that in which of the 2 to the n states you're actually in. And now we'd like to ask, well, these are our states. What can we do with them? In particular, can we perform some unitary operation in this Hilbert space? So suppose I initialize the system somehow in some state. How can I go to another state? Okay, so how can I do that in a controlled way? Doing any local measurement anywhere or any local operation, if you hit the system somewhere here, that's actually not gonna do anything within this Hilbert space. You're gonna stay in the same state essentially. Okay, so you might excite some stuff here, but that's not what you want. You actually want to do things slowly. Suppose the rules of the game are going to be that we want to stay within the subspace, but we want to somehow move from one state to the other. So how do we do that? Well, I mean, a way to do that is braiding or exchange. Okay, as we discussed, these vortex cores are like point objects. Okay, the vortices themselves are extended, but the vortex core is a localized object, and you can ask, well, suppose I have some experimental knob that allows me to actually move these vortices around each other. Okay, such that at the end of this process, I'm going to be I'm going to tune it such that the Hamiltonian of the system actually went back exactly to itself. So that means that the vortices have just exchanged positions and the vortices are identical. So the Hamiltonian is the same, but the state of the system doesn't have to come back to itself. Okay, so it can change, and this would exactly realize some unitary operation acting on these states. And the interesting thing is that this unitary operation is not going to depend on the exact way I do this. Okay, it's only going to depend on the topology of this path. Okay, so this is what we're going to do. Now, it's kind of easy to imagine how to do that in the case of a vortex in a P plus IP superconductor, because you can sort of imagine moving this thing around. It's a little bit more tricky if you think about these wires, but it's actually there is a well-defined protocol to do that also there. Okay, and that's kind of important because the wires are much closer to being experimentally realized, as we discussed. Okay, so actually demonstrating this in experiment is actually something that people are seriously pursuing now. In some sense, this would be the ultimate demonstration of non-abelian statistics in the lab, which would be really a precedence. I mean, there's no that's people have been talking about for many decades, but there's no direct experimental demonstration of that. Okay, so what I want to derive is basically this unitary transformation that I get from exchanging two of these vortices, okay, or two of these, you can think about them as quasi-particles. So I exchange two quasi-particles. What unitary transformation acts within this 2 to the n over 2 Hilbert space? And it turns out that it's very simple. There's a very a compact way to write it down. So let me start from writing it down, and then I'll try to derive it in a couple ways. Okay, so it turns out that right. So the operators that are at my disposal, the physical operators that actually act within this Hilbert space, are the Majorana zero modes. Okay, so in each of these vortices, there's a fermionic. There is a real fermionic operator gamma 1, gamma 2, all the way to gamma n. Right. So yeah. So as we demonstrated, also, okay. There are actually subgap states living at the boundary. Okay. So what I'm gonna do for now is imagine that this boundary is very far away. Okay. If it's very far away, there's no way it can actually physically matter. Now, are there corresponding Majorana zero modes at the boundary? Right. That's what you asked. So suppose there are even numbers of these vortices. So there are actually no exact zero modes at the boundary, okay, for a finite system, but the system is large, so the spectrum at the boundary is essentially continuous. Okay, so I just want to keep myself far away from the boundary, so I don't need to discuss it. Or if I'm a theorist, I can imagine that the system is on a sphere and there's no boundary. Okay, then there would have to be the same number of anti-vortices, but I'll also keep them far away. Okay. Right. So good. So I can basically form this Hilbert space, this 2 to the n over 2 Hilbert space, using these Majorana zero modes. Okay. So I can construct, actually starting from some reference state, I can construct all the other states. It's just a Fock space that I can construct using these Majorana zero modes, and I should be able to write this operation in terms of the Majorana zero modes, and there's actually a very simple expression for that. Okay, so in this case, if I just exchange number 1 and number 2, okay, and do nothing to anybody else, then the operation that I get can actually be written very simply in terms of the operators gamma 1 and gamma 2. Okay, now right. So what is this? So this is a matrix, okay? So it's a matrix that acts on this 2 to the n over 2 Hilbert space, and this matrix is diagonal, commutes with the operator I gamma 1 gamma 2. Okay, so this is a bosonic operator, 2 fermions. Okay, its eigenvalues are just plus or minus 1. Okay, and you can check that this operator squares to 1. So basically, each one of these states has an eigenvalue. And what this matrix does, it just gives the state a phase that depends on this on the eigenvalue of this operator. Okay, so the phase is either e to the I pi over 4 or e to the minus e to the I pi over 4, depending on this value of the state. Okay, and it doesn't depend on anything else. It doesn't depend on the eigenvalue of gamma 3, of I gamma 3 times gamma 4 and so forth. Okay, so I'll refer sometimes to this operator as the fermion parity that you can define using the operators 1 and 2. Okay, P1, 2. So this a unitary transformation depends only on P1, 2. Okay, and you can ask, well, what's actually non-abelian about this? This just looks like a phase. It doesn't actually change the state. If I give you a state which is an eigenstate of I gamma 1 gamma 2, this doing this braiding operation would not actually change the state. It would just give it a phase, okay, which is either pi over 4 or minus pi over 4, and that is correct. Okay, but it's correct in a particular basis. It gives a different phase to different states. So if I use, for instance, a basis of eigenstates of a different operator, say a gamma 2 times gamma 3, okay, this would be a different basis. So this is also an operator that has eigenvalues plus and minus 1. Okay, and these two operators don't commute, so I can't actually diagonalize them together. I'll show a more explicit example of that later on. Okay, and then in this basis, if I choose for some reason to work with, if I prepare the system in a state which is an eigenstate of this operator rather than that one, and I act with this braiding, I'll find that if I start from the state which has eigenvalue plus 1, I'll actually go with some probability or some amplitude to a state with the eigenvalue minus 1. Okay, so it does actually change the state. Yes? Yeah. I'm going to derive it. Right.
That was exactly the question.
Okay. Right. So now I've given you the answer. Now my goal is to derive it in various ways. Okay, or motivate / derive it. Okay. Right. So this is why I call this non-abelian, and actually this goes through, so I can exchange any pair. Okay. What happens if I do a more complicated exchange? So suppose I exchange a 1 and 2, but actually there's number 3 over here. Okay, then there's something else that happens. There's a different unitary matrix that would depend also on 3. I won't write it down. I can, if you're interested, I can explain how to think about this. But for now, let me just imagine that I just exchange a pair in a path that doesn't enclose any other vortex. Okay, so now one comment. Okay, so I was sloppy here. I didn't write, as we discussed at some point, I didn't write the overall phase here. Okay, so this is a unitary matrix that can have a phase, and in fact, when we talk about fractional statistics, usually if it's abelian statistics, the whole point is that this phase can be different from 0 and pi. Namely, these particles are not bosons or fermions. Okay, so this is an abelian phase. This is a phase which is independent of the state. Okay, all the states get the same phase. Now, here exactly comes the subtlety that we mentioned as we went along. Okay, this state, the P plus IP superconductor, for instance, and for sure the 1D Majoranas, are not true topologically ordered states. Okay, in the following sense, the vortices in the P plus IP superconductor are not point-like particles. They have long-range interactions. If I exchange two of them, I actually cannot really sharply define this overall phase. Okay, whereas if I there are models such as the Moore-Reid state and for a filling fraction of 5/2 in quantum Hall, where there's a very similar structure. These vortices or things that are very analogous to these vortices appear, but they're really truly point-like particles, and the non-abelian part of the exchange has the same structure, has the same form, but this phase is actually well defined. Okay, you can really define what this phase is precisely. Okay, so it's an exchange phase, it's some Berry phase. It has a definite value and will have a definite value in depending on the state you're in. Okay, so it's actually not enough to specify the non-abelian part in general. Okay, but here this is all I'll have. I'll have only the non-abelian part in both of these cases. Okay, this is sometimes referred to as a projective representation of the braid group. Okay, so they're all the braiding operations that I can make. Each one of these operations, exchanges of any pair, can be represented as a unitary matrix. So that's a representation of a group. Okay, so it has a structure of a group. What I have here is not actually a representation of the group. It's only a projective representation of the group, which means that I can I basically have an uncertainty about the phase here. Okay, I can't define everything is defined up to an overall phase.
Yet this state is independent of the state.
The part of the phase which is independent of the state, that's the part that I won't define.
Yeah.
Okay.
I mean that these log interactions.
Exactly. That's the important part. Okay, there are long range interactions between vortices that give some energy that depends on the position of the vortices, but this energy does not split this degeneracy. Okay, it's blind to which of the 2 to the n over 2 state you're in. Okay, that's a crucial point. Yeah. The braid group. Okay, I'll describe a little bit more later. Okay, so it's basically but just in a word. Okay, you have some point like objects, and you arrange them on a line arbitrarily in some order, and an element of this group would be exchanging 2 of them in some order. Okay, you imagine that they're on a line, but they can move on a plane and return to the line. Okay, so this would be one element, and then you can do it again. Okay, and so forth. You construct, basically, you have all the pair exchanges, and any sequence of pair exchanges is an element of your group. Okay, the unity is not doing anything. You have an element in its inverse. Okay, you braid like this or like that, and so forth. Yes, projective up to a phase. Okay. Right. So yeah. So more on that later. Now, yeah. So now let me argue for this form in a couple ways. Okay. So there's a kind of a more heuristic argument, and then there's a way to derive it, and it's actually nice to think about these wires in that context. So right. So there's a nice argument by Ivanov, 2001. Which basically says the following. Okay, so it's kind of very pictorial, not very precise, but very pictorial. Okay, so you say, let's take 2 of these vortices, and rather than asking what happens to the state of the system, let's ask what happens to the operators. Okay, so I have gamma 1 and gamma 2. Now, I sort of imagine that I have my control parameter and my Hamiltonian. I have a Hamiltonian that depends slowly on time. And what this time dependence does is basically just pushes this vortex over here and that vortex over there, such that the end Hamiltonian is equal to the original Hamiltonian. Okay, so there's some time dependence, some adiabatic evolution operator. And I can ask what is the solution of the Heisenberg equations for the 2 operators of the 0 modes, gamma 1 and gamma 2. Okay, so if you like, there's some evolution operator, okay, which is function of t, and I can ask, well, what happens to gamma 1, and what happens to gamma 2 as a function of t. Okay, so right, so this operator eventually would become this U12, almost by definition. Okay, that's one way to think, at least, about this U12. You just change the positions of the quasi-particles slowly in time and ask what's the evolution operator on the state. Okay, and as you know from the Adiabatic Theorem, there's a dynamical phase and there's a Berry phase. And here the Berry phase is actually a Berry matrix. It's an Abelian Berry phase because our states are multiply degenerate. Okay, so there are actually many low energy states. The rate in which I do this is much slower than the gap and so forth, but it's bigger than the tiny splitting between these states. Okay, so we can sort of argue what this transformation does to the operators on the basis of the following argument. Okay, so what are these things? Well, these things are fermions, that live in vortex cores. Okay, so now what's a vortex? So as you recall, okay, as we sort of did last time, we actually described a vortex as a branch cut in the phase of fermions. Okay, so a vortex is a 2 pi phase winding for Cooper pairs. So you can do a gauge transformation. You can undo that 2 pi phase winding at the price of introducing anti-periodic boundary conditions for fermions. Okay, so a fermion that goes around a vortex actually undergoes a pi phase shift. Okay, so you can think of about each one of these vortices as follows. Okay, a vortex is just a branch cut where if fermions cross this branch cut, then they undergo a phase change of pi. Okay, so of course the position of this branch cut is unphysical. Okay, we chose it by the way we do the gauge transformation. Okay, the only thing which is gauge invariant is that if a fermion, say an excitation of the superconductor, went all the way around the fermion, a vortex, then it would the total Berry phase it would acquire is pi. Okay, this is very closely related to the things that Subir was talking about. Okay, so this vortex is like the Weizmann in a Z2 a topological phase. Okay, now in a Z2 spin liquid. Okay, so right, so now we can sort of guess the answer. Okay, so this is what Ivanov did. So basically what we do under this exchange. Okay, so one thing we know is that gamma 1 somehow at the end of the process should be proportional to gamma 2. Okay, because just this operator kind of got dragged along. We know how to track it at every intermediate stage, and at the end, there's no other room for it but to go to gamma 2. Okay, and gamma 2 better go somehow to gamma 1. Okay, but the only remaining thing to determine is actually the sign. Okay, so this is, say, proportional to gamma 2, and this is proportional to gamma 1. Okay, but remember that these are real fermions. In principle, you may have thought that there could have been a phase here, but these are real fermions, and they remain real fermions under the unitary evolution. So the only freedom left here is to determine the phase. Okay, so we basically exhaust the possibilities by saying that gamma 1 should go to plus or minus gamma 2, and gamma 2 should go to plus or minus gamma 1. And the question is which option is actually realized by doing this exchange. Yes? Right, so that's a good question. Okay, on the basis of locality, I argue that this cannot happen. Okay, so think about it like this. Okay, so this gamma 1 is some mode of the Hamiltonian. Okay, and this gamma 2 is some other mode. Now they're exactly degenerate, so you're actually absolutely right in worrying that you might end up in some linear combination. Okay, but but this one, I'm always gonna make sure that during the entire path, this one is much further away than that on the units of the microscopic length psi. Okay, so more technically speaking, okay, you would say that these are split a little bit. These are not the true eigenmodes of the system. The true eigenmodes are exactly superpositions. Okay, but the splitting between the even and odd superpositions, say, is e to the minus L over xi. And as long as I do my operation fast compared to that small energy scale, okay, then they won't mix. If I start from one, it won't go to the other. Okay, the only way of it to leak to the other is through their overlap somehow. And that's very small. Right, so I have to do it, I have to take some time window. Okay, so I have to, there's some a characteristic time that I do this. Okay, so 1 over t, that has to be bigger than this energy. That has to be fast. Yeah. Okay, and it has to be slow compared to the gap. Okay. Right. Yeah, and this of course raises a lot of questions. This is not the only. In practice, if anybody really tries to do this, this is probably not the limiting factor on the speed. Okay, there would be, in reality, the system is at finite temperature. There's some non-equilibrium population of quasi-particles, and they would destroy this process, and you have to be fast compared to that, and so forth. Okay, but for now, this is our only concern. Okay, so sorry.
You're calling the one from the left gamma 1, and at what point does it change its character?
Right. So it's yeah. Right. So this thing is living in a superconductor, right? So there are actually many other modes. There are modes that I don't write because they're at high energy. But when I move this thing around, okay, somewhere along the way when this is here, okay, so in terms of the original operators, this would be some superposition of some other operators which are not these two at all. Okay, and then it just changes its character until it becomes gamma 2. So I'll do later a more explicit example where you'll actually see this happening. Yeah.
Maybe a stupid question, but if you have to do it fast, then don't you have to worry about the friction, by density and friction of your body?
Yeah. So I do, but I won't. Okay. So right. So this is coming back to this question of the Goldstone modes. Okay. So the system is not really gapped in reality. But then, then I'll argue, well, let's do that in a superconductor. Now, it's a 2D superconductor, but let's put it on top of a 3D trivial superconductor. And then, and then the system is really gapped. Okay, so, or let's do this in a Mouride state, which is totally gapped. Okay, right. Okay, so, right, so now the picture, which is kind of very nice, very a little bit cheating, but very nice, is the following: that each one of these vortices carries this branch cut, and as I move these two around, okay, so the way I've chosen the branch cut, one would actually have to cross the branch cut of 2, but 2 actually doesn't cross the branch cut of 1. Okay, so the way, okay, or the other way around. Okay, so 1 goes around from the top, but 2 has to collide with the branch cut of 1. Okay, so this means that gamma 2 actually, relative to gamma 1, acquired this actual minus sign here.
What if one bridge cut goes down and the other goes up?
Did I do it the wrong way? So the one went from here.
What if one bridge cut goes up?
Right. Yeah. Then it would be the opposite. Sorry. Did I mess this up? So let's see. Right. So yeah. So if I do this, then I didn't return to the same Hamiltonian. Okay. So I have to be a little bit careful. So right. So you would say the following: the position of this branch cut is a gauge choice. Okay, so by doing a gauge transformation, I can change it around. Okay, so now I can choose this as you propose. Okay, so such that the branch cut of 2 goes down here and the branch cut of 1 goes up. Okay, and then let's do this. Okay, so then I follow it, and I end up in a picture like this. Okay, so now physically everything's fine. I return to the same Hamiltonian up to a gauge transformation. Okay, but if I want to compare the states that I got in the beginning at the end, I have to undo this gauge transformation. Okay, I have to correct for that, and I'll have to do a gauge, a change that would bring the branch cuts to their original position. Okay, and I claim that when I do that process, I'll actually necessarily get this extra minus sign back. Okay. Right. So yeah. So this is the argument. Now, yes. That's right. That's right. Okay. So that's right. I can even if I make sure that at the end I go back to the same gauge, okay, to the same Hamiltonian written in the same gauge, okay, I can choose whether to do it like this, such that 2 would cross the branch cut of 1, or do it the other way around, such that 1 would cross the branch cut of 2. This would actually make a change, a difference. Okay, it would actually enter as a sign here, and this minus sign would move over there. Okay, so there are actually two operations which are distinct in 2D. I can exchange clockwise or counterclockwise, and these are different operations. Okay, so yeah.
So is this equivalent to just considering an unknown of Bohm phase of the magnetic flux?
Right. So an important point here. Okay, so these are neutral particles. Okay, there's actually no magnetic field here. Okay, so for this purpose, it's not an Aronoff-Bohm effect. It's true that it's as if one particle is sort of carrying an effective flux for the other, but this is some sort of emergent flux. It's not the physical magnetic field.
So, but then is it correct to say that although this sign depends on the choice of the path that I take, but any observable that I would calculate
Yes.
shouldn't matter?
Yeah, right. And you can even say which one gets a plus and which one gets a minus is kind of arbitrary, but the fact that if I go like this and if I go like that, I'll get an opposite phase, that's not arbitrary. Okay, so this is what we got for the operators. Okay, but what we wanted is the operation on the states, not on the operators. Okay, so we have to somehow show that this is necessarily equivalent to that, and it turns out that it is. It's kind of easier to show, of course, the other way. Okay, so my claim is simply that if you just explicitly take this unitary matrix U12 and act on gamma 1. Okay, you'll get gamma 2, and if you take U12 and act on gamma 2, you'll get minus gamma 1. Okay, and I'll leave this as an exercise. It's very simple because exponentiating this matrix is kind of very easy, right? Because I gamma 1, gamma 2 is either plus or minus 1. So it's very easy to exponentiate. So you can really do this in 3 lines and get it. Yeah. Right. Yes. Right. So I agree. It's not trivial. That's the whole point. I mean, you can check that this indeed leads to that, but I'll show you a direct way to actually derive this. Okay, to actually derive this, including the pi over 4. Just to complete the comment. Okay, so if you want, an easy way to understand why pi over 4. Okay, so write it as e to the I theta, some unknown phase, times okay, so without the I. This I is not there. Sorry, this I is a typo. Right. Yeah. Gamma 1, gamma 2. Okay, and then you can express this easily for any theta. Then just stick it into here and require that gamma 1 goes to something proportional to gamma 2, and that actually fixes the phase to be theta equals pi over 4. Okay. Yeah, there was another question. Yeah.
So you're saying that, for example, if you look at the path which doesn't cross any branch cuts,
Yeah.
then you're saying gamma 1 goes to gamma 2.
Yes.
That's the path.
Yeah.
And it sounds plausible, but I mean, it sounds like you're using some kind of continuity argument.
Yeah.
At the same time, we don't know what the Majorana mode looks like in between. So
Exactly. Yeah. So right. So we don't know how the Majorana operator looks like in between. It actually depends on the path how it looks in between, right? So if I chose a different path, somewhere here it would look very different.
So you're somehow assuming that the sign is everywhere defined along this path, and I don't see how.
Yeah. So that's exactly right. That's continuity essentially. Okay. So now I mean right. So there's a subtlety here. The sign is not defined anywhere along the path. So you can say the following. I can track this operator continuously, given a path, right? So that I can do, and if I do that, I just have some operator gamma of t. Okay. Now this operator always has a freedom which is plus or minus 1, but that's fixed by continuity, right? Because of the fact that it's not a continuous phase, right? So usually when you think about Berry phases, then you say, well, if I don't close my path, then the phase is not well defined because I can redefine the phase of my states, of my basis anywhere along the path. Here I'm tracking operators, not states, and these are these are Hermitian operators, so I can't multiply them by an arbitrary phase. Okay, so this sign is in a real way is actually well defined given a path and given a gauge.
But I guess you can't really conclude whether it's plus or minus or plus.
Yeah, I can't. Yeah, yeah. I can only say that there's a relative sign. No. So the reason for that is the adiabatic theorem. Okay, so that's the only available state around at zero energy. Okay, all the other states are above the gap, are separated by a gap. Yeah, but right. So this comes back to this assumption. Okay, all the other vortices far away are localized very far away. Okay, so the evolution is local. So now I'm assuming that my rate is fast enough such that I don't resolve. So the true eigenstates of the system are actually superpositions of these gammas on different vortices. But as long as I go fast enough compared to that splitting between the even and odd, then there's no way this thing is going to tunnel. Okay, there's a time scale. If I start from an operator at time equals 0 here, there's some time scale of beating with other vortices. Okay, but as long as I'm fast compared to that time scale, and that time scale is exponentially long in the distance, then it's not going to end up somewhere else. Okay, so that's my requirement here. Okay, here's kind of a slightly better argument. Okay, so it's basically what I've been asked here. Okay, so what I claim is the following. Well, I don't know what this matrix exactly is, but either way, okay, so I've exchanged these two vortices 1 and 2, and there's a fermion parity that I can define using 1 and 2. That's this P12 operator. Okay, so now I haven't involved any other vortices, as was discussed. Okay, all the other vortices are really far away, so they're not going to be the result of this operation cannot possibly depend on any other gamma operator but these two. Okay, so it can't depend on gamma 3 times gamma 4 and so forth. More technically, you can say I could have done this operation with some gamma 3 here and gamma 4 there, but I could also take them far away. Okay, there's no way this operation can know whether there's some other vortices some long distance away. Okay, so this unitary matrix has to be some function of the operator I gamma 1 times gamma 2. Okay, it cannot depend on any other observable within this subspace. This phi, well, okay, so this phi we're at the moment not worrying about, right? So in fact, sorry. That's right. This is completely independent of the phi, right? So this is why this is something I like to talk about, right? Because this phi I don't know anyway. Right. Okay. But right. So it has to be some function of gamma 1 times gamma 2. Okay. Now it's a unitary matrix. This operator is a Hermitian operator, and its eigenvalues are just plus or minus 1. Okay. So there's not a lot I can actually write. This is basically the only thing I can write. Okay, and if you work it out, what this transformation would look like for a general theta, it would just bring gamma 1 into some linear superposition of gamma 1 and gamma 2. Okay, and gamma 2 into a linear superposition, orthogonal linear superposition of gamma 1 and gamma 2. Okay, and then if I just require that at the end of the process, gamma 1 has to be proportional to gamma 2 and gamma 2 to gamma 1, okay, then I basically fix this angle. Okay, it turns out to be pi over 4. You can do it. Okay, so right. So finally, I want to say something about how to derive this a little bit more rigorously, and it also relates to the question. Well, this is all easy to think about in terms of vortices. It's a little bit more tricky to think about it in the wires. Okay, so suppose I have my n over 2 wires. Okay, and so forth. Each end has a Majorana 0 mode. And I want to exchange, say, 1 and 2 in some way. Now, right, now, what do I do? These things live on a line. Each pair lives on a line. So what do I even mean by exchanging them? Okay, so So right, so just exchanging two things on the line is not very well defined. It turns out that what I need in order to do that is to introduce some auxiliary modes. Okay, so let's consider this kind of setup. Suppose I have my wire, and here are my two Majorana 0 modes, gamma 1 and gamma 2. And let me imagine that here there's another wire. Okay, and this one has gamma 3 and gamma 4. Okay, so now if I don't let anybody interact with anybody, I basically, or if I don't start moving somehow things around, deforming the system in some way, there's no way I'm going to be able to exchange gamma 1 and gamma 2. But once I introduce other modes, then I'm going to be able to do that. Okay, and the way to think about it is very similar to what we actually discussed for the vortices. Okay, so I can't describe the path using only gamma 1 and gamma 2. I have to recall that somewhere along the way, okay, gamma 1, well, when I move this vortex around, gamma 1 just moves over here. So now the 0 mode in this intermediate state along the path is actually written in terms of some other Majorana modes that used to be at high energy, but now went all the way down to low energy, while this one becomes gapped. Okay, so I have to mix my Majoranas with some other auxiliary Majoranas in order to perform this operation. So this is precisely what I'm going to do here. Okay, so let me imagine. Okay, and it's actually even experimentally, it's not so far-fetched to think that you have some knobs that allow you to control the coupling between different Majorana modes. Okay, so the way this was first envisioned, so it's a paper by Alicea and company, okay, from 2011. So they said, well, I mean, we know that we can induce the topological transition between the trivial and topological phase using a gate potential. So let's assume we just have an array of gates here, and we can control them. So we can basically shift the end of this wire around. Okay, and then if these two Majoranas become close compared to the coherence length, they're going to become coupled, and they're going to gap out from 0 energy. Okay, so they're not 0 modes anymore, and that's useful because now I have my auxiliary Majoranas. I can try to maybe have an evolution that moves this one over here, and then moves this one over there. Okay, so this would facilitate the exchange for me. So that's basically what I'm going to do. Okay, now it's very interesting that the way people actually imagine doing this today is not by changing the gates by controlling the length of the wire, but actually by controlling the Coulomb interaction in the system. Okay, so these are two different parity states of electrons, but if the wire is very long, they have exactly the same charge. But as Abel here can tell you, I'm not sure where he is. Once these become close, they actually the Coulomb interaction actually becomes important. It actually lifts this degeneracy between the states. Okay, so that might be a knob that would be useful to do that. Okay, so but anyway, it doesn't matter for our purpose now. I'm just going to imagine that I can control the coupling between different Majorana modes at will. Okay, and I have 4 of them, and I want to somehow exchange 1 and 2. Yes.
What do you mean by Coulomb interaction?
Right. So it's not the Coulomb interaction between the Majorana 0 modes because there's no such thing. They're neutral objects. Okay, it's basically how much so on this wire there's some charge which is fluctuating. Okay, now if it's coupled to a big reservoir, like a big superconductor, then this the energy hardly depends on this charge. Okay, so there's no that's what I mean by no Coulomb interaction. Whereas if you somehow close it to the outside world, suppose that there's this wire which is a tiny superconductor. Okay, so it's a mesoscopic system and there's some charging energy. Okay, so that's what I mean. Okay, so it's like how much, what's the energy, total energy dependence of the ground state on the number of electrons in the system. Okay, so but I'll not worry about that for now anymore. Okay, so what I'm going to do is just write down a time-dependent Hamiltonian But and I'm basically assuming the following. I'm assuming that I have my system that has a gap to all the excitations except these four. Okay, these four are at low energy. 1 and 2 start their lives as zero modes. 3 and 4 start their lives coupled. Okay, so I only have 2 zero modes, but I have my 2 auxiliary modes that are at finite but small energy compared to anybody else. So I can write down an effective Hamiltonian, effective low energy Hamiltonian, only in terms of gamma 1 through gamma 4. Okay, so it's going to be a time-dependent Hamiltonian, and it's just going to be written this way. Okay, so a sum over all the pairs, and I have some j, gamma I, gamma j. Okay, and this j depends on time in some prescribed way. Okay, so what I'm going to do is, instead of describing the braiding as a path in position space of vortices, I'm going to describe braiding in parameter space. Okay, so I have these parameters j, and the braiding is going to go on. It's going to take place in this parameter space. Okay, but other than that, it's a conceptually straightforward problem. I just need to find the adiabatic evolution operator within this space. Okay, and it's a very easy problem because it's a finite dimensional space. Okay, it's 2 to the power n over 2. N here is 4, so it's just a 4-dimensional Hilbert space. That's all. Okay, so it's easy. Now, one thing to note. Okay, so now it leaves us with the question: what path should I actually take? Okay, what path should I actually choose? And of course, there's a constraint. Okay, so in order to get a universal answer, what I have to make sure is that at any point during this path, so this h effective of t during any intermediate time actually has exactly 2 zero modes and everything else is gapped. Okay, because if I didn't do that, and at some point during the process I actually introduce another zero mode, so I closed the gap to the 2 auxiliary ones, then I'm not guaranteed that I would actually end up in this state that I want. Okay, then all my arguments at any given time around any given zero mode, there are no other zero modes to mix with, so my result is unique. That's not going to be true anymore. Okay, so what that means is that I have to make sure that there are 2 and only 2 zero modes at any given time. Okay?
My Hilbert space is 4-dimensional.
Right.
And if I have 2 zero modes, this is exactly 4 states.
Right. Yeah. I mean, it's 4 states overall. So 2 ground states and 2 excited states. That's what I'm going to have.
Oh, you mean I want to have one wire at 0 energy and the other one initially is far away.
Right. Okay. So that's what I want my spectrum, my many-body spectrum, always to look like this. Okay. So I have my 2 degenerate ground states formed by these 2 Majorana zero modes. Okay, 2 Majorana modes are a 2-level system, and I want 2 excited states, and I want these 2 excited states never to go all the way to 0. Okay, and moreover, I mean, the interesting thing is that, of course, it's a very big parameter space, and I expect my result not to depend on the exact path that I take. Okay, so just like in the case of the vortices, I argued that the result of this operation doesn't depend exactly on how you do it. It should be a topological property. So I'll have to argue that this is the case here somehow as well.
Sorry, but why do you write these 2 excited states at the same energy and not at the E and the minus C?
Right. So that's an important point. I'm plotting here not the solution to the Bogolubov-Dejean equation. I'm actually writing the many-body Fock space states. Okay, these are many-body states. These are not the eigenmodes of the Bogolubov equation, which indeed would look very different. Okay, they would look like this. Okay, so it's taking these states, forming a Fock space, and filling it. Okay, in all possible ways. Right. So there's a nice protocol how to do this, and it's kind of when you after you think about it, it's very, very intuitive. Okay, it looks like this. So at first, our initial Hamiltonian is going to look like this. Okay, so this is 1, 2, 3, and 4. So I'm going to have the coupling between 3 and 4, which is non-zero, and all the other couplings are 0. Okay, so that does the job, right? Because I have 1 and 2 that are decoupled from anything else, so they're exactly at 0 energy, and 3, 4 split off from 0 energy. Okay, so now I need to somehow move these 1 and 2 around. I need to do something to the system. So I need to somehow couple the 3, 4 somehow to gamma 2 or gamma 1. Okay, so let me start by coupling it to gamma 2. Okay, so for instance, I can do something like this. Okay, this is 1, 2, and this is my starting point, 3, 4. Let me also turn on some non-zero coupling between 2 and 4. Okay, so this is J3, 4. This is J2, 4. So this is also non-zero. Okay, so what happens? Well, right. So I might worry that when I do that, I might actually lift this degeneracy. Okay, which is something that I never want to do. So I have to make sure throughout the way that the ground state is always doubly degenerate. Okay, because if it's not doubly degenerate, the two states, the two ground states in my Hilbert space are going to acquire some dynamical phase, which is not going to be universal. Okay, so the phase difference that they acquire would be not in my control. But this actually doesn't happen. As long as 1 is always decoupled from 2, 3, and 4, it turns out that I can actually couple 2, 3, and 4 in a completely arbitrary way. So these J3, 4 and J2, 4 can be anything, and the spectrum would still look like this. Okay, so there still are 2 degenerate states. Okay, and there are various ways to argue that. There's kind of a nice way. Okay, the important thing is that during this process, 1 is always completely decoupled from 2, 3, and 4. As long as I maintain that, the Hamiltonian of 2, 3, and 4 can be completely arbitrary. Okay, and here's the argument for that. So I need to consider what symmetries my Hamiltonian has during the way. Okay, and it actually has 2 symmetries. So what commutes with the Hamiltonian? Well, the total fermion parity of the system definitely commutes with the Hamiltonian. So I have the parity operator, which is just the product of all the gammas. Okay, so this commutes with H effective. And this would commute with H effective always, okay, independent of what Hamiltonian I write. That's just because any term that I write here is either a 2 fermion, or even if I write a 4 fermion term, that always commutes with this. As long as I don't put an extra fermion from the outside in the system, this is going to be conserved. Okay, so this is an assumption. It's going to be approximately true if the system is at low temperature. There are no quasi-particles above the gap. Okay, but in the way I've chosen to do it, during this process, okay, if I turn on any coupling between 2, 3, and 4, there's actually another conserved operator, which is just gamma 1. Okay, so gamma 1 never appears in this Hamiltonian, and therefore it's also going to be conserved. Okay, so gamma 1 is also conserved. Okay, but now I have two symmetries of my Hamiltonian. So 2 operators that commute with the Hamiltonian, but don't actually commute with each other, right? So the fermion parity anti-commutes with any of the fermion operators, so it anti-commutes with gamma 1. Okay, so that means that if I found a ground state with p equals +1, if I act on that ground state with gamma 1, that would flip the eigenvalue, and it has to remain a ground state. Okay, so the ground state is actually twofold degenerate always. Okay, for arbitrary coupling between 2, 3, and 4. So that's the key argument, and that actually gives us a guide of what we should do. We should always make sure during this process that there's one Majorana mode which is decoupled from all the others. Okay, and as long as we do that, this structure of the spectrum would remain. There are 2 fold degenerate ground states, and moreover, it's something that's not so hard to imagine doing experimentally. Okay, you just need to make sure that there's one Majorana mode which is always far away during this process. Yes. Yeah, yeah. So that's right. So this is why I drew these two, the excited state as twofold degenerate as well. Right, yes.
The other zero mode is not localized. You cannot stay
Exactly. Right. So if I have a Majorana zero mode gamma 1 and I have a conserved quantity P, that means that there's necessarily another fermionic zero mode, which is just gamma 1 times P. Okay? So that's the other zero mode. You can say gamma 2 times gamma 3 times gamma 4. That's a fermionic zero mode, has an odd number of fermions, and it commutes with the Hamiltonian. And it's indeed, as you say, it's a mixture between all of these three. Okay, so I can say what I've done is I've taken my free zero mode gamma 2, coupled it to some system, so it delocalized over the system, but it still has to remain a zero mode. Okay. Right. The next thing I'm going to do. Okay. So remember this. Okay. So I started with a coupling between 3 and 4, and I turned on a coupling between 2 and 4 at the same time. Now I can turn off the coupling safely between 3 and 4. Okay, so at the end of step number 1, okay, so this is this to here from here. This is step number 1. What I have is the coupling 4 to 2 being non-zero, and all the other couplings are 0. Okay, and now this is gamma 3 and this is gamma 1. Okay, so I see that when I do that, what I've essentially done, okay, if I did what I advertised before, so I solved the Heisenberg evolution equation for the operators, what would necessarily happen, I claim, is that if I track the evolution operator for the operator gamma 2, at the end of this step number 1, it would go to what used to be gamma 3 in the original basis. Okay, so essentially what happens is that this one moves over here. Okay, and then it's kind of clear what to do, right? So eventually I want to exchange 1 and 2. So from here I'm going to go to this configuration. Okay, so these are 1, 2, 3, and 4, and I want to move 1 to 2 now. Okay, so the way I can do that is turn on a coupling between 1 and 4, with the coupling between 2 and 4 on, but keeping gamma 3 far away, such as that's not coupled to anything. So as long as there's one free Majorana, which is not coupled to anything else, the ground state degeneracy is going to remain, and the gap is going to generically remain. Okay, so what I do is just simply move this coupling over here. Okay, so now 1 and 4 are coupled, and 2 and 3 are zero modes. Okay, so that's step number 2. Okay, and then the last thing I need to do is to move this one back to there. Okay, so I turn on this coupling. And at the end of this process, the Hamiltonian actually goes back to its original form. Okay, so it goes back to J34 being on, and everything else being off. But I argue that this operation, okay, so it's some path, it's some closed path in parameter space, but I claim that this operation is equivalent to actually braiding, to actually exchanging gamma 1 and gamma 2. Yes? Right. So yeah. Right. So what the constraints are basically the following. So first of all, I have to do this adiabatically. Okay. So I have to do this adiabatically compared to this gap, because if I don't, then I'm going to lose. I'm going to excite my system. The system is not going to remain in either of these ground states. It's going to end up in some excited state with some probability. Okay. That's the first constraint. The second constraint is precisely this point, that I have to be able to set while I mess up with 2, 3, and 4, say I have to set gamma, so J1 with everybody else, I have to set it to exactly 0.
So I mean like for each one of these steps, like when you have two couplings on,
Yeah.
I can have the two couplings different, and that's still
Yes.
fine. Like there's
Yeah.
always a time at which one goes to
Yeah, yeah, right.
policy.
Yeah. Right. So for instance, there's this step, right? So 1, 4, and 3 are all coupled together. There might well be also a coupling between 1 and 3 in this case, okay? Because once they're coupled, there's no reason for 1 to be coupled to 4 and 4 to 3, but not 3 to 1, right? So all of these couplings can be on at once, and moreover, their values can be totally arbitrary. Okay, and my claim is, that's not obvious, but my claim is that the result is going to be completely independent of that. Okay, so.
If I have any three levels and I couple them like this, then I don't necessarily, I mean, I have some population, let's say, almost it, I don't necessarily, it's not necessarily that all of it is going to go to be at any point.
It is. Right. I'm doing everything adiabatically. Okay. Right. So take again. Right. Take this step. Right. So I started with 1 being here, and 2 and 4 are coupled. Okay. So there's of these 3, there's 1 0 mode. Okay. So think about the BDG spectrum. So there's 1 0 mode and 2 away from 0. Okay, now I changed my Hamiltonian adiabatically. I rotate somehow this wave function, but there's always 1 0 mode exactly. Now at the end, there's also 1 0 mode. It's just that the 0 mode lives at 2, not at 1. Okay, so what used to be at 1 has to go to 2. There's just no other state it can go to. Okay, so and that's completely independent of how I did this in parameter space, as long as I do it adiabatically.
Real operations, when you set the coupling to 0, you have to do it adiabatically.
I have to do everything adiabatically. Yeah.
You slowly turn off the coupling.
Yes. Right. Okay. So that's the trouble with this thing. It's not the best operation. There are other protocols that have been proposed that instead of changing things adiabatically, rely on actually measuring, doing measurements on the system. Okay, so doing a non-unitary. This is all unitary evolution. Okay, you can also achieve the same thing by doing a sequence of non-unitary operations that comes with its own problems, but at least it doesn't have to be adiabatic. Okay, so that's a limitation here. It will have to be slow. Okay, but just to prove the concept, it's good enough. Okay, so how does one actually analyze this? So, yeah.
So in this step, when you have the 0 mode delocalized between 2, 3, and 4,
Yes.
is it still, so you claim that now there is a 0 mode which is Majorana and gamma 1, and the other one is gamma 1 times p. Is that what I understood?
That's correct. I mean that is true. I mean there is a 0 mode which is just 2 times 3 times 4.
But
In
this is no more a Majorana, right? Gamma 1 times p.
right, so it's a fermionic 0 mode. Okay, so it's not it's
So these are really Majoranas. I mean, you're
right. So
Majorana, but then you don't have another Majorana 0 mode anymore.
yeah, so I mean in fact in the solution of the stated Hamiltonian, there is actually also something that you would be more comfortable calling a Majorana 0 mode. Let me actually demonstrate that in a moment, okay? But there would also be some linear combination of 2, 3, and 4 that's actually gonna remain a 0 mode. Okay, but yeah, in fact, if you think about it, there's no reason not to call gamma 1 times gamma 2 times gamma 3, or gamma 2 times 3 times 4, not to call that the Majorana 0 mode. It's a fermion, okay? I can arrange that to be Hermitian. That squares to 1. I can arrange that to square to 1. Okay, so yeah, if I put the right factors of I in the right places, I can arrange that to look exactly like a Majorana mode. Okay, so there's nothing special really about having a single versus 3, any odd number. Okay, so right. So yeah, let me just sketch how you actually analyze this problem. Okay, so that's possible to do in various ways. The kind of simple and nice way is to just parameterize the Hamiltonian in step number 1. Okay, so step number 1 is the step where we turn on gradually the coupling between 2 and 4. Okay, so we'll have some parameter h of lambda. Okay, and this parameter is going to be minus j. Okay, so 1 minus lambda times the initial coupling. Okay, so I gamma 3 times gamma 4. And then I want to couple 2 to 4. Okay, so I'm going to add to this, parameterize this, minus lambda times j. And then I gamma 2 times gamma 4. Okay, so this is my parameter-dependent Hamiltonian, and I'm going to vary this parameter lambda as a function of time gradually from 0 to 1. Okay, so this goes from here to here. So right, so now what I'm going to look for is a zero mode as a function of lambda of this Hamiltonian. Okay, so for instance, at lambda equals 0. Gamma 2 doesn't appear in the Hamiltonian, so it commutes with the Hamiltonian. Okay, but once I turn on lambda, gamma 2 is no longer a zero mode. However, if you think about the Bogoliubov-de Gennes equation, okay, so this is a quadratic problem. So there are 3 modes here, and they have to come in pairs of E and minus E. So since there are 3, 2 of them are going to be split away from 0, but 1 is always going to remain at 0. There's just no other choice. Okay, so for any lambda, there's going to be some linear combination. Okay, so there's some gamma of lambda that's just the sum over all the 3 Majoranas. Okay, 2, 3, and 4. There's some linear combination that's going to remain a zero mode. Okay, so what I'm looking for is to solve for these coefficients such that this actually commutes with the Hamiltonian. Okay, and that's very easy to do. Okay, so I just make use of the fact that the commutator of gamma 3 with gamma 3 times gamma 4 is equal to twice gamma 4 and so forth. Okay, so I can just plug this and solve for these coefficients. Okay, so it's done in the notes. Okay, and what I'll find is basically that there's an equation that relates. Okay, so it turns out that the A3 here is always 0. There's some equation that relates the A2 and A4. Okay, so right, so that basically tells me what the wave function of the zero mode is as a function of lambda. Okay, so if I did this right, let's see, for a lambda for a lambda equals 0. Okay, so I just have A4 equals 0, A3 equals 0, so the zero mode is actually on A2. Okay, so that's my initial state where this is completely decoupled, so the zero mode is here. And now I change lambda. For any lambda, there's some linear combination. Okay, and for lambda equals 1, which is the end of this process, I see that A2 actually has to be 0, and A4 it doesn't have to be 0. So the zero mode actually moved to A4. Right. So at the end of this process, 2, 4 are on, and 3 is decoupled. I think the labels here are messed up. Okay, so right, so this I turn on the coupling between 2 and 4, and 3 at the end is actually decoupled. Okay, and you see that if I track this thing, because of the fact that the lambda evolution is continuous, I can actually track the sign of these coefficients. Okay, so I actually know not just that the zero mode has moved from from 2 to 3 in this case, I can actually determine the sign. Right, so this I can do throughout this process, basically. Okay, so this is a way to solve for the evolution of the zero modes, and there's also a way to do it for the actually for the states, but that I won't describe. Okay, to actually find the unitary operation at the end, the U12, on the Hilbert space. Okay, so it's possible to do it using the same, just solving this problem. Okay, right. So if you do it, it's kind of a nice exercise. You can show very easily that up to a sign, gamma 1 goes to gamma 2 at the end, and gamma 2 goes to minus gamma 1. Okay, so you just track what happens to the zero modes at every intermediate step.
Can I ask a question?
Yeah.
How is this related to the operator gamma 1 multiplied by p, which you said is also a zero mode?
Right.
Is something. How is it related to this linear combination?
Right. I basically always have, right, so think about the original Hamiltonian, right? So I have gamma 1, which is a zero mode, gamma 2, which is a zero mode. I have, I mean, it's a symmetry. It commutes with the Hamiltonian, right? So gamma 1 and gamma 2 commute with the Hamiltonian, and I have the product of all four, which also commutes. Okay, so basically any combination of these operators would also commute. Right, now what is, for instance, gamma 1 times gamma 3 times gamma 4? Okay, so gamma 3 times gamma 4 times I, that's the Hamiltonian. Okay, so in the ground states, that is just a number. Okay, so that's one way to understand what is this product.
So just gamma 1 by pi is always during the process. It is also a symmetry set.
Yeah, right. So
It's not a zero mode.
during step number 1, sorry, I may have messed up the terms. Okay, it commutes with the Hamiltonian. It's a symmetry.
Okay, but it's not the operator of the zero mode. The operator of the zero mode is in the combination.
There are two, right, so, so there are two symmetries, there are two operators that commute with Hamiltonian. Okay, during this process, gamma 1 always commutes, and there's some linear combination that depends on lambda, but it always exists that also commutes. Okay, and in particular, there's also the product of all 4 times 1, which means the product of 2, 3, and 4, which also commutes. Okay. Sorry? Right. So what we're saying is that at any intermediate stage step during this process, there's gamma 1 which always commutes with Hamiltonian. Okay, so gamma 1. Okay, there's some particular linear combination of 2, 3, and 4, which we can solve for this particular Hamiltonian. Okay, so that's kind of the non-universal part. Suppose there were n other Majoranas here, all gapped, but they can all couple to these 3 during the process. There would be some combination of them, which is a symmetry. That would depend on the particular Hamiltonian. Okay, the only thing we're guaranteed is that there is some combination, which is a symmetry. Okay, so there's this gamma of lambda, which is a symmetry. Okay, and that's basically all we need here. Okay, so right, so that's a systematic way to derive this this braiding rule. Right, so now let me see what how am I doing on time? Still have right. Oh, I have 10 minutes. Okay, so in 10 minutes, then I'll skip a little bit ahead. Right. So yeah. So I'll basically just give a little bit of overview of what I was planning to do to say, and with that I'll finish. So yeah. So just two issues. Right. So the first issue, yeah, the issues are somewhat related. So the first issues is I've kind of demonstrated everything using non-interacting, so quadratic Hamiltonians, and I've actually claimed that this is much more general. Okay. So even in the presence of interactions, if I added quadratic terms to my Hamiltonian, the basic structure would remain. Okay. So the question is, of course, why? And moreover, there's another question. Okay, so I kind of argued that for quadratic Hamiltonians, there are in one dimension. There are two distinct phases. One of them is the topological phase, and the other one is the trivial phase. And the question is, of course, well, I mean, quadratic Hamiltonians are convenient, but let's add some arbitrary interactions. And what would actually happen? Do I get a richer structure? Okay, so can I get more distinct phases that I don't have access to using a quadratic and fermion Hamiltonians? Okay, so let's sort of go back to our Majorana chain. Okay, so we had a Hamiltonian, okay, which was written in terms of some fermions on the lattice. Okay, some hopping and some pairing. Okay, and some chemical potential. Okay, and we've mapped out the phase diagram of this Hamiltonian, but now let's add to it any sort of quadratic interaction and ask what actually happens. Okay, so first of all, do these zero modes that I find somehow survive, or do they just disappear when I add quadratic interactions? And second, if I look at any local Hamiltonian of this family, would I get a richer phase diagram? Okay, maybe there's some phases that I just can't access without turning on some four-body interactions. Okay, and for one dimension, the answer to that is pretty well understood. Okay, so we think that the answer is first of all, the phase of the topological 1D superconductor actually survives even in the presence of interactions. Okay, this phase is well defined basically as long as you have fermion parity conservation. Okay, so what does that mean? So what that means is that the many-body spectrum, the presence of quadratic terms. So now I can't draw the single particle Bogoliubov-de Gennes spectrum anymore, but I can still talk about the many-body spectrum. So as long as I don't close the gap, okay, suppose I turn on some interaction here, U. So as long as this U is not so large that it actually collapses the bulk gap, this is actually gonna, the basic properties of this phase are basically gonna remain the same. Okay, so my many-body spectrum is gonna look like this. There are two states that are very close in energy, okay, up to an exponential in the system size. These two states have an opposite fermion parity. Okay, so they're just like the states that I labeled before by gamma 1, gamma 2. Okay, equals plus or minus 1. And they actually differ by the total fermion parity of the system. And the rest of the spectrum is separated by these two by a finite gap. Okay, now there's a subtlety here. These two are going to be almost degenerate. The rest of the spectrum is kind of at least the high energy part of the spectrum would be harder to talk about, okay, because it's a very, very dense spectrum. So I can't really say whether the high energy states in the spectrum are come in pairs like the ground state or not. Okay, I won't worry about that. It's only the low energy part of the spectrum that's going to have this structure of coming in degenerate, almost degenerate pairs. Okay, right. Moreover, what are actually gamma 1 and gamma 2 in this case? Okay, is there something that replaces gamma 1 and gamma 2? Okay, or is there some operator that actually commutes with the Hamiltonian in this case? Okay, when I add interactions. So, right, so the answer is that there would be some operator that would replace gamma 1 and another that would replace gamma 2. Okay, they would be different. They would be even different in the quantitative sense. Okay, so there would be some gamma left. Let's call them gamma left and gamma right. Okay, some operators that live on the two sides. and this gamma left is still going to be a Hermitian operator. Okay, and it's still going to be a fermion. It's still going to be a fermionic operator in the sense that it's going to anti-commute with the fermion parity. Okay, so it's going to contain an odd number of fermionic operators in terms of these psi's. Okay, and it's going to have some structure like this. It's going to be some psi plus some psi dagger. But then because of interactions, it doesn't have to be a linear combination of psi's and psi daggers. It also can contain some component with some coefficient here, which is not universal, okay, which looks like psi dagger times psi times psi. Of course, all of these come with some spatial coefficients, plus Hermitian conjugate, okay, plus a phi fermion term and so forth. Okay, and there could even be psi, psi, psi. Okay, this doesn't conserve the number because the Hamiltonian doesn't conserve the number. Okay, but as long as I didn't close the gap, I claim that this operator is still going to be localized somewhere around the left edge. Okay, so the support of these operators is gonna be close to the left edge. They're going to decay exponentially into the system. When you go any component that includes an operator far away from the edge is going to decay. And there's going to be another one that corresponds to the right boundary. Okay, and right, and what do these operators actually do for us? Okay, so I would like to write this. Okay, that there are symmetries. Now that's not quite right, but there are symmetries in the low energy part of the spectrum. Okay, so in the low energy subspace, these approximately commute with the Hamiltonian. Okay, in other words, if you project them to these two states, then they commute. Okay, so and moreover, the total fermion parity of the system in the low energy subspace is going to be given by I gamma L gamma R. Okay, so much of the same structure remains, but only at low energy. It's not at the level of operator identities. It's operators projected to low energy. These would satisfy much of the same rules. Okay, so that's for the first question. Okay, now the second question: are there actually other phases in one dimension that would give us a richer structure? Okay, so take any Hamiltonian. Suppose that the gap closes and reopens, and you go into some new phase. So can we get qualitatively new physics that way? Well, the answer is that in one dimension, as long as we don't have any other symmetries other than fermion parity conservation, the answer is no. There are only these two phases. Okay, so to get something richer than Majorana fermions, you actually have to go at least one dimension higher. Okay, so right, so there are various arguments and various level of rigor for this, but we strongly believe this is true. And finally, let me just say a word. Okay, so I won't be able to really talk about it, but there's kind of an intermediate route. Okay, so you could actually find richer things. You can find fractionalized versions of Majorana modes if you go sort of half a dimension higher. So what I mean by that is the following. Okay, so think about the edge states of some 2D system. So right, so imagine the following setup. Okay, so this is a big 2D droplet of some 2D phase, say a fractional quantum Hall state, which is in a Laughlin state, say at a filling fraction of 1/3. Okay, so now let's cut the system in two. Okay, so let's imagine a trench cutting through the system. Now, a fractional quantum Hall state, just like the P plus IP superconductor that we've discussed, actually has a chiral edge mode, which is running around it. Okay, so on every edge, there's an edge mode running like this. Okay, this edge mode is described by a 1 plus 1 dimensional conformal field theory. Okay, it's interacting. It's not something that you can construct without interactions, but it still it allows a very simple description. Okay, so for many purposes, it actually the degrees of freedom that live on this trench look a lot like the 1D wire that we've discussed. Okay, there's one mode moving up and one mode moving down. If you then look very closely, this just looks like a quantum wire, just like we had before. Okay, so the Majorana wire. Okay, but the thing is that this thing is not a 1D wire. It knows that it actually lives on the boundary of some fractionalized phase. Okay, and now what you can do, in the same way that you did for the wire, you can actually gap out this edge. Okay, once you have two counter-propagating edge states, you can gap them out, and you can gap them out in various ways. Okay, you can allow electrons to backscatter from one wire to the other. Okay, so there's some operator in this edge theory that describes backscattering of electrons. Okay, so you backscatter one electron. There's some amplitude here, m. Okay, and under the right conditions, or if this m is large enough, you can argue that this would actually open a gap at the edge. Okay, once this opens a gap, what it does, it's plausible physically, what it really does is just heals back this droplet over here. Okay, so if this backscattering is strong enough, somehow the system is going to gap. For sure, there's one way to gap it out. It would just retrieve the integrity of the quantum Hall droplet across this trench. Okay, so that's one possibility to gap the system out. But it turns out that there's a distinct possibility, and that's kind of, you can guess that from the analogy to the 1D wire. You can actually couple the system to a superconductor. Okay, so if you have another term in the edge Hamiltonian, which is psi r dagger, psi l dagger. Okay, so suppose there's some region here. So this is a region where you have backscattering, and this is another region where you couple the system somehow to a superconductor. Okay, how to do that is another question. Okay, it's conceptually simple, but of course there are many practical considerations here. But let's leave that aside. Okay, so if you do that, it turns out that you would also gap out the edge. In fact, there's a duality that relates these two regions on the edge which are gapped. Okay, so these are dual to each other, but nevertheless they're distinct. Okay, and this is like your wire coupled to a superconductor, gapped by a superconductor, and it's, if you like, it's surrounded by regions that are trivial, that are just insulating. And in an analogy to the wire, you would expect to actually find new kinds of zero modes that live on this boundary. Okay, and these zero modes, in some sense, would be fractionalized analogs of the Majorana zero mode. Okay, and what are these zero modes? Okay, so what are these zero modes of, and what are their properties? So it turns out, okay, so the Majorana zero mode is a zero mode for electrons. Where you have a Majorana zero mode, you know that you can actually inject an electron from the outside at zero energy cost. So that's actually what the experiments typically detect. Okay, so what is this zero mode? Well, I mean, it's a zero mode for electrons too, but it turns out that it's a zero mode for Laughlin quasiparticles. Okay, so this is basically its defining property that you know that at the bulk of the system you can get fractional charge excitations. Okay, in this, if it's 1/3, you can get E/3 quasiparticles that have fractional statistics. Okay, and it turns out they have a gap everywhere in the bulk, but it turns out that you can actually inject one of these at this boundary at zero energy cost. Okay, so that's the special property of this zero mode. Moreover, just like the Majorana zero mode, this